Hello everyone. Today we will study electricity, the fundamental of power, from source to socket. जो इलेक्ट्रिसिटी उसका सोर्स क्या है? आज in present time there is a we move to renewable source of electricity generation. For example, like energy is transformed, not created. Forms like solar, wind, nuclear, and hydel energy are converted into electrical energy, go through the transmission lines, then power grids distributed to how residential area and industrial areas. There are in between socket and sources there are conductors and insulators. Conductors are manufactured with copper, allow electricity to flow easily, and insulator rubber do not. The language of electricity. Two types of electricity, two types of current, AC versus DC. AC alternating current, reverse direction homes. DC direct current flows one way like batteries. There are such a terms: voltage denoted by capital V, current denoted by capital I, resistance denoted by capital R. First we understand voltage, the force or pressure that pushes electrons to flow, unit volt. Current, the rate of flow of electric charge, electrons, unit ampere A. Resistance, the opposition to the flow of current, unit ohm. Now, in previous parts we have studied about Government of India has launched national program of LED based home and street lighting. Now we move to power factor. Power factor. In AC circuit, various components are connected, such as resistor, inductor, capacitor. These components consume power. When voltage is applied to an inductor, it opposes the change in current. The current is built up more slowly than the voltage, lagging in time and phase. In this way, it can be stated that current lags voltage. In case of capacitor, voltage depends on the charge. In this case, flow of current transfer the charged electron. In case of flow of current transfer the charged electron to the plates of the capacitor, after which a voltage gets established across the plates. When inductor or voltage do not peak at the same time, the fraction of a period difference between peaks are expressed in degrees and is known as phase difference. The phase difference is less than 19 degree. Because of this phase difference in voltage and current, power in capacitor and inductor will be minimum, or it can be said that the circuit will lose this power. This power is called as reactive power. In case of resistor, the both current and voltage are in the same phase. Therefore, power applied to the resistor will get utilized. This power is called real or true power. Combination of true power and reactive power is called apparent power. There is a diagram 1.16. Power factor is the ratio of real power apparent power. Value of power factor varies upon 0 to 1. It is denoted by cos theta. Power factor real power divided by apparent power. Referring to figure 1.6 1.16, it is observed that as the reactive power starts reducing, the real power and apparent power become equal. When real power and apparent power become equal, so it means that the AC circuit is resistive in nature. It will only have a resistive component in the circuit. At this time, it can be summarized that the reactive power due to capacitor and inductor will not get utilized by the circuit. Apparent power is the total power given to the circuit. Reactive power is the unutilized power, and real power is power utilized by circuit. So before moving to the next topic and put some effort on doing our assignment, we move to our short video related to our chapter. That's
powers our entire modern world, but let's be honest, most of us just take it for granted. It has no sound, no smell, we can't see it. So what is this mysterious energy really? In this explainer, we're going to peel back the layers on one of the most fundamental forces in our lives. You know, in its most raw form, electricity is just spectacular. It's this powerful natural phenomenon. I mean, just think of a thunderstorm. That lightning you see, that's pure electrical energy. A massive, totally uncontrolled discharge that just reminds you of the sheer scale of the forces at play in our universe. But here's the crazy part. We've somehow managed to take that wild, untamed force and domesticated it. We've channeled it into this huge, intricate network that brings light and power right into our homes. So today, we're going to explore that incredible journey, from that raw, natural power to the simple flip of a switch. All right, first up, our world on wires. We call it an invisible power, but you can bet our dependence on it is very visible. We've built our entire society on this quiet assumption that this force will always be there, flowing silently behind our walls and under our streets. Really? Just picture it for a second. The power goes out. Suddenly, hospitals can't run life-saving equipment. Banks freeze up. Transactions stop. Our own homes just go dark and silent. It is absolutely not an exaggeration to say that electricity is the lifeblood of modern civilization. So, section 2, from energy to electricity. Okay, if electricity is so important, where does it all come from? Well, the key thing to get is that we don't just, poof, create it out of nothing. It's all about transformation. It's a fundamental principle of the universe that lets us turn one form of energy into another. Yeah, it all comes down to one of the most basic rules in all of physics, the law of conservation of energy. This is the absolute core principle behind all power generation. We aren't making energy, we're just changing its clothes, so to speak. And we've got all sorts of places to get that starting energy. We can take the heat from nuclear reactions, or the kinetic energy from wind and water, or of course the radiant energy from the sun. And we convert it. No matter how complicated a power plant looks, it really just boils down to two simple steps. You take a primary form of energy, say thermal energy, and you transform it into the incredibly useful and transportable form we call electrical energy. All right, time for section 3, the atom's secret power. So we've seen how we convert energy, but that still doesn't tell us what electricity actually is. And to find that answer, we have to go from the massive, sprawling power grid down to the microscopic. We're going to zoom way in. We've seen what it does, we know we rely on it, but we still haven't answered that big question. What is it? Like, what is actually happening inside that copper wire? Well, the answer starts right here. Everything, you, me, this screen, the stars in the sky, it's all made of atoms. And the secret to electricity, it's locked away deep inside this tiny, tiny structure. Right at the heart of the atom, you've got the nucleus. And that's made of positively charged protons and neutrons, which have no charge. But orbiting that nucleus are these teeny negatively charged particles called electrons. And these little guys, they are the absolute superstars of our story. So this whole positive and negative thing, that's a basic property of all matter, and we call it electric charge. And like any property, we need a way to measure it. The unit we use is called the coulomb. It's the basic yardstick we use for quantifying electricity. So, 1 coulomb, what does that even mean? It's the total charge of about 6.25 quintillion electrons. That's a 6 followed by 18 zeros. I mean, that number is just mind-bogglingly huge. It really tells you just how tiny and numerous these particles are. When we talk about electricity, we're talking about wrangling these massive, massive armies of electrons. Okay, let's move on. Section 4, making the current flow. So get this, everything around you is already packed with these charged electrons. But just having them sit there, that's not electricity. The real secret, the key to the whole shebang, is getting them to move in an organized way. You need to create a flow. So on the left here, in a normal piece of wire, the electrons are just bouncing around all over the place. Totally random, so they don't really go anywhere. But then, on the right, you see what happens when we hook up a power source, like a battery. We give them a push, and suddenly they all start flowing in the same direction. That organized flow, that is what we call an electric current. Of course, not all materials let this happen. Think of conductors, like copper, as a crowded dance floor where electrons can easily switch partners and move around. But insulators, like the rubber on the outside of a wire, they're like strict chaperones, holding on to those electrons for dear life, stopping the flow completely. And you need both to control electricity safely. And that brings us to our final section, voltage, current, and resistance. Now that we have a current, we need to know the rules that govern it. This whole flow of electrons is controlled by 3 fundamental ideas. Get these 3 concepts down, and you basically understand how all electricity works. Let's start with voltage. The absolute easiest way to wrap your head around this is to think of water in a pipe. Voltage is like the water pressure. It's the force, the push, that gets those electrons moving. Higher pressure pushes more water, right? Same idea. Higher voltage pushes more electrons. Okay, so if voltage is the pressure, then current is the actual flow. It's a measure of just how many electrons are zipping past a single point in the wire every second. In our water analogy, this is how much water is actually gushing through that pipe. And finally, we have resistance. This is basically electrical friction. It's the opposition that slows that flow down. In our pipe analogy, this is like a kink in the hose or a really narrow section of pipe. The narrower the pipe, the higher the resistance, and the harder it is for that water to get through. So, let's recap real quick. You've got voltage, the push, measured in volts. You've got current, the flow, measured in amps. And you've got resistance, the opposition, measured in ohms. And the key thing to remember is these 3 are always in a dance together. You can't change one without affecting the others. So, seriously, the next time you just flick on a light switch, pause for a second. You're not just closing a circuit. You are commanding an invisible army of quintillions of electrons to march through a wire, all to light up your room. It's not magic, it's just physics. And it's happening all around you, all the time.
Hi there. So this is a overview of our chapter. So let's go through a flow diagram. Fundamental of electrical and electronics. First, we see electricity basics. Electricity definition: physical phenomena of electrical charge. According to the sources, electricity is defined as a set of physical phenomena associated with presence and flow of electric charge. The charge is a basic property of subatomic particles, specifically electrons and protons. In the larger context of electricity basics, the source provides the following insight to the nature of electric charge. Foundational property of charge: subatomic particles. All matter is composed of atoms which contain proton, electron, and neutron. Protons carry a positive charge and electrons carry a negative charge, and neutrons are neutral. Attraction and repulsion. A key physical phenomenon of charge is that opposite charge attract each other while same charge repel each other. The attraction between positively charged protons is the nucleus and negatively charged electrons in their orbits hold the atomic structure together. Now, modern electricity basic modern importance appliances, cars, essential device, electricity basics types. There are static, stationary charge, stored energy, dynamic current, moving charge through conductors. After that, we move to atomic structure of electricity, electrical and electricity. Atomic atoms building block of universe. Center containing proton and neutrons, subatomic particles, electric charge proportional to imbalance electrons in Coulomb. Electrical quantities: current I, flow of charge measured in ampere, voltage, potential difference measured in voltage, resistance, opposition to motion measured in ohm, power, rate of work measured in watt. Material: conductors lose electrons, easy flow, copper, aluminium. Insulator: tightly held electrons, high resistance, rubber, glass. And we have some assignment related to this. Now we move to our first assignment, that is related to electric circuit parameters. Voltage, current, resistance, power. The circuit consists of 9 voltage 9 volt battery, a fixed resistor of 3 ohm, and a 5-watt bulb or LED connected in series. Most common simple circuit for such school experiment as shown in typical Fig 1.17 for class 9 to 10th physics textbooks. Important note about the components: a normal small 5 watt incandescent bulb, if that's what it means, has very low resistance when cold, 2 to 5 ohm. So connecting it directly with only a 3 ohm resistor to 9 volt would draw very high current, 1 to 2 ampere or more, making the bulb extremely bright or burn out quickly and draining the battery rapidly. This is not a practical for a safe school experiment. A 5-watt LED is also unusual. Typically small LED are 0.1 to 1 watt. High power 5 LEDs need special heat sinks and current limiting and normally operate at a much lower voltage, around 3 to 12 volt depending on type and dedicated drivers. There are calculation steps. You can take the screenshot of it. There are 6 steps. Second assignment. The second assignment require analyze the live, neutral and earth ports of a power socket. This is critical aspects of electrical safety and understanding household wiring. Residential cables typically contain a live wire, a neutral wire and an earth wire. The live wire carries the alternating current AC from the power source of the appliances. It is the most hazardous part of the circuit because it maintains high potential difference relative to the ground. It many wire standards. The live wire is typically colored brown or red. The voltage on these wires can be measured using a non-contact voltage measurement method. In single phase system, the live wire carries a full phase voltage, typically 230 voltage or 120 voltage depending on the region. So this is the we have a picture of appliances that use in neutral wire. The neutral wire complete the circuit, providing a return path for the current from the appliances back to power source. Earth wire. The earth wire is safety feature designed to protect a user from electric shock. It provides a low resistance path for fault currents to flow directly to the ground, bypassing the user in the event of an electrical fault.